Okay, welcome to the first video from Chapter 12, Simulations. The purpose of this video is basically to kind of introduce simulations and then, more importantly, explain why we do them. So the easiest simulation I can show you is that of rolling a die. So I'll roll two, what the heck. Die one, die two, okay? And Excel actually has a function that mimicates rolling a die. That function is the rand between function. And here, all you have to do is put in a bottom and what they call a bottom and a top number. So if you think about rolling a die, the smallest number you can roll is a 1, and the largest is a 6. So I'll put in a 1 and a 6, and voila, Excel randomly generates a whole number between 1 and 6, right? So this mimics rolling a die. Oh, and by the way, every whole number between 1 and 6 is equally likely, right? So the rand between function mimics a discrete uniform distribution, which is exactly the distribution that a die roll comes from. So there you go. I mean, basically, there's a simulation. I've just simulated rolling a die. And then, of course, if I copy this over, I get a second die roll, okay? Now, the reason I want to show you this is, whoa, the first die changed, right? What happened here? Well, the rand between function and some of the other functions that we're going to be using are what they call volatile functions, and you'll see that right here. Formula resolve equals volatile. Well, what this essentially means is that anytime you do something in Excel, and you have like this rand between function, Excel will randomly generate a brand new number for you. So if I just hit OK, you know, there you go. It's going to now it's randomly generating both die rolls, all right? So I'm going to show you how to fix that in just a minute. But basically, there is a very simple simulation. Now, I could copy this all the way down and simulate over 1,000,000 die rolls, all right? And I'm going to do that in just a minute. But first, I want to talk about why. Why do we do these simulations? Well, basically, it's all it's the result of the central limit theorem. So I'll explain this sheet in just a minute, but hopefully you remember from your stats class the central limit theorem. And what the central limit theorem tells us is two very important things. First, just so long as my sample size is 30 or more, right? Then if I get a sample of 30 or more and calculate the average of that sample, that average will be normally distributed, all right? And furthermore, the expected value of that sample average will equal the true population mean, all right? And that is what I want to show you in this sheet. And to show that to you, I'm going to run some simulations, or I'm going to run a simulation and show you that indeed the sample mean is normally distributed, and the expected value of the sample mean is equal to the true population mean. So to do that, I've got my the distribution for a single die roll, right? So here x, my random variable, f of x is my probability. And of course, with a die roll, I have 6 random variables. And then notice that each random variable is equally likely. So I've just taken 1 divided by 6. Again, that's why we say die rolls follow a discrete uniform distribution, because the likelihood of getting any number from a die roll is the same, right? 0.17. Okay, so if you remember, hopefully you remember from your statistics course, that once I've been given the distribution for any random variable, I can calculate the expected value for that random variable. And the expected value is simply a weighted average of my sample outcomes, right, the 1 through 6s, weighted by the probability that each outcome is going to occur. So the easiest way to calculate your expected value is just to use the sum product function. So I'll just take the sum product of my random variables and the sum product of my probabilities, hit OK, and voila, there you go. So the expected value of rolling a die is actually 3.5. So what does that mean? Right, that means that before you roll a die, you would expect to get a 3.5. Now I know it's impossible to get a 3.5, but you can get stuff like this, like the expected value of a 3.5, even though the 3.5 isn't a part of the sample space. That is possible to get, when you're dealing with these discrete distributions. Obviously, when you go to a continuous distribution like the normal distribution, that you're not going to run into that problem, right? But you can do it, or you can have that in these discrete distributions. Okay, at any rate, the bottom line here, what I want you to understand is that the expected value of a die roll is 3.5. All right? So now what I'm going to do is this little thought experiment. Well, if I roll 2 die, what are the possible outcomes? And I've got them all listed here. And I'll make this a little bit smaller so you can see a few more. All right? But at any rate, I could get I can get a 1 on the first die, and then 1 through 6 on the second die. I can get a 2 on the first die, and then of course 1 through 6 on the second die, right? And I just keep repeating that. 3, 1 through 6, 4, 1 through 6, 5, 1 through 6, 6, 1 through 6. All right? And then, so I roll these 2 die, right? What I should say is here are all of the possible outcomes from rolling 2 die. There are 36, okay? Well, what would happen then if I took the average, right? So I'm going to roll 2 die and take their average. Well, here would be all of the possible outcomes I would get by taking the average, all right? So what I want to show you here is what possible values for the average are there. And you may already know this, but I'll show you a quick and easy way to see it. I'm just going to sort by average, and here you go. So the smallest average I can get by rolling 2 die is a 1. And then I get a 1.5, I can get a 2, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, 6. So what this is telling me is that if I roll 2 die and take their average, right, these are all of the possible outcomes that I can get for the average, all right? So now what I want to do is I want to go back to this sheet and I want to simulate rolling over 1,000,000 die, taking their average, right, and then graphing that, right? So according to the central limit theorem, the average of 2 die rolls should be normally distributed, and the expected value of that sample average should equal the true population average of 3.5, right? This is the population average for a die roll, right? Because this just comes from the actual distribution itself. So this is mu, right? Mu is the population average, that's 3.5. And so now I want to simulate rolling 2 die, taking their average, and showing you that in fact, that X bar is going to be normally distributed, and the expected value of X bar is equal to the true population mean. So to do that, we're going to run a simulation. So I need to calculate the average of my 2 die roll. Oops. So I'll calculate that real quick. Hit OK. And now what I'm going to do is I'm going to copy this, this row all the way down. So I'm going to have over 1,000,000 observations. So we'll copy this. all the way down. Like this is as far as you can go in Excel. There are only 1,048,756 rows in Excel. So I'll go ahead and paste. This will take a few minutes. That won't take a few minutes, but give poor Excel some time. It's thinking. All right, there you go. So I have just replicated rolling 2 die over 1,000,000 times and calculating their averages. Now I still have a problem though, because as I mentioned before, the rand between function is a volatile function. So now that I have my 1,000,000 die rolls, right, I don't want these die rolls to change anymore. So to do that, I'm going to do a copy paste. So highlight your die rolls. There you go. And then go to copy and then hit the down arrow on paste and paste the values. Okay, let's let Excel think for a minute. There we go. So what that does is when you hit paste values, Excel takes the last value that's in that cell and makes that the new entry in the cell, right? Because my point is, this used to be the rand between function, not anymore. Now it's just the values, and in fact, it was the last value that was in the rand between function, right? So that's what pasting the values does. Okay. Well, at any rate, so here I have my simulation, the 2 die roll and their average. And now what I need to do is, well, what I want to show you is I want to show you the graph of the averages, okay? So I can do that really quick. Based on our previous discussion, we know that these are the only possible outcomes for this average, right? So I can get a 1, and then I can get a 1.5, and then I can get a 2, 2.5, 3, 3.5, 4, 4. I went too far. No, perfect, spot on. Okay, so here are all of the possible outcomes that these averages can take. Okay. Now, of course, going back to your stats class, what I want to do now is count all of the ones in this column, right? Because that's going to give me my frequency distribution, right? So let's do that. So I'm going to use the count function, right? So, wrong function. Count if, my bad. Count if. All right, so the range are my averages from my simulation. Okay, and then the criteria. So what do I want Excel to count? I want Excel to count all of the ones in this range. All right, and so there are 29,034 ones in this column C. So now what I'm going to do is I want to anchor my range, but not the criteria. And I'm just going to copy this down. And voila. So here is my frequency distribution. This tells me how many ones I got in my simulation, how many 1.5s I got, so on and so forth. So if you go back to your statistics course, graphing the frequency distribution, that's actually the probability distribution for this. So let's just graph this. Insert, graph. Oh, perfect. Move so you can see it better. Move the chart to a new sheet. And voila. Now, I hope you understand. Look, this is a normal distribution. Now, I admit it's not continuous, but that's because a die roll is not continuous. But you can certainly imagine a line, right, going up, coming over. I mean, this is about as normal as you're going to get. Now, furthermore, I want you to understand a few things. and this is one of the reasons we do simulations. If you can do this at home, and you will get a graph that looks exactly like this, right? Now, when you do this at home, you're going to get different die rolls than I did, right? Because these were all randomly generated. But the central limit theorem guarantees that this is the distribution you're going to get, okay? Now, remember that this is the distribution for X bar, right? Here is X bar. This is the average. So this would be trial or simulation 1, or random sample 1, I get an X bar of 2. Random sample 2, I get an X bar of 4, so on and so forth. So this chart is the distribution of X bar. And what I'm trying to get at is the distribution for X bar is normally distributed. That's exactly what this chart looks like. It looks like a normal distribution. All right. Now the next thing that I want to show you is that the expected value of X bar is equal to the true population mean. All right. Now remember that the true population mean is 3.5. So if I go in here, so right now I just have 1, 2, 3, 4, 5, up to 11. I don't have my variables down here in my horizontal axis. So let me just change those. So I don't want these. I want my horizontal axes to be these numbers, right? These were the numbers that I graphed. So let me highlight those. Let me hit OK. Hit OK again. And voila, look. The 3.5, so this is X bar. This is the X bar of 3.5. That has the highest probability of occurring. In other words, the expected value of X bar is equal to the true population mean. So what this is saying is that, right, again, what do you expect to get when you roll 2 die and take their average? You expect to get the population average of a die roll. All right. Now I know that I'm using, these are actually the frequencies, okay? But if you don't like that, I can always change this into probabilities to make it more formal. So to do that, all I have to do is sum up my number of observations. All right, and then this is going to give me my relative frequency distribution. You might remember that from your stats class. Divide that by this. Anchor the total number of trials or simulations that I have. All right. So in other words, what this is telling me is that there is basically a 3% chance of getting a 1. So in other words, if I roll 2 die and take their average, there's only a 3% chance I'm going to get a 1 for an average. And so let me just copy this down. Okay. Again, a 3% chance I'm going to get a 6 for the average. And you'll see how symmetrical this is. Let me back out a little bit so I can get more on the screen. Oops. All right. Okay, there you go. So look at how symmetrical this is. Let me just go to comma format. Look, right? 3, 3, 6, 6, 8, 8, 11, 11, 14, 14. And then lo and behold, what's the most likely outcome of this distribution? The 3.5. The 3.5 is the population mean, all right? And this is my point, right? If you think back to your stats class, the normal distribution is perfectly symmetrical. Well, lo and behold, at least rounding to 2 decimal points, I have a perfectly symmetrical distribution. So again, I'll graph the relative frequency distribution for you, for those that are used to seeing that, right? So all of these numbers here are going to change. They're all going to become between 0 and 1. And I still get the same graph. And then let me redo these horizontal axes labels. hit OK. Come on. Okay, well, there you go. So lo and behold, what have we shown? We have shown, using simulations, we have shown that the sample mean X bar follows a normal distribution, just like the central limit theorem says that it will. So essentially, I've just kind of, shown you the central limit theorem in action. And then secondly, I have also shown you that the expected value of the sample mean is equal to the true population mean, all right? So that's what this is, right? This is the expected value of the sample mean because this is the distribution for the sample mean, right? And this is the expected value because it's the most likely value to occur, right? And again, so the expected value of the sample mean is 3.5. Well, here we learned that the population mean of a single die roll is 3.5, right? So in other words, the expected value of X bar is equal to the true population mean. Now, it turns out that that is probably, the fact that it's normally distributed and the fact that the expected value of X bar equals the population mean, that's why we do all these simulations. And, in the next 2 weeks, I'm going to go through various problems with you. But the whole point of running the simulations is to do something like this, run a simulation 500 times, 1,000,000 times, whatever it is, and then calculate the average, right? Because now when I calculate that average, so that would be the X bar, right? That average is going to be our best estimate of the true but unknown population mean. So for example, in financial planning services, right, one of the big things that you guys come up with or that you got to deal with, if you will, is clients aren't worried about returns in the past. They're worried about future returns. Well, we can use simulations, right, to estimate future returns. And then, just imagine having 500 simulations. We take the average of those 500 simulations and we say, look, right, the expected value of that average is equal to the true population mean, right? So we believe that the market, is going to return, say, 10% next year, and that's going to be awful close to the true population average. That's what all of this is about. And that's why we run simulations, because we're trying to predict, say, what next year's return in the stock market is going to be. We're trying to predict what the volatility is going to be next year in the stock market. Well, we're trying to predict whether or not there'll be a recession when your clients are retired, right? 5 years into retirement, if a recession hits, what does that do to their retirement portfolio? Do they have enough to survive or to make it, blah, blah, blah. That's what we're going to do with these simulations, all right? So with this first video, I know I've gone a little bit longer, but it is absolutely imperative that you guys understand that X bar, the sample average, right, is normally distributed. Secondly, the expected value of the sample average is equal to the true population mean, right? Therefore, we say that X bar is an unbiased estimator of the population mean. So again, if you think back of simulating next year's return in the S&P 500, if you have a simulation, say like 500, so your sample size will be 500, and you take the sample mean of those 500 simulations, well, that X bar is going to be an unbiased estimator of the true but unknown return for next year, all right? And that's the reason we do all these simulations. Okay, well, that's enough for this video. In the rest of these videos for Chapter 12, I'm going to go through just a few more complicated ways to simulate stuff. Now, with that said, I don't want you to get freaked out. This was a very simple simulation, probably the easiest one that we have. The rest are fairly simple. We just have a few tweaks that we can do to simulate more than just a discrete uniform distribution. All right? All right, well, that is it for the first video.